Hi, my name is dr.ahmath. In this video lecture, we are going to discuss about diagonalization. This is one of the ways of factorizing the matrices using the eigenvalues and eigenvectors. So I would like to start this lecture with discussing a problem where we need to find the eigenvalues and eigenvectors of this 2 by 2 matrix. And throughout this lecture, we are going to use this matrix as an example matrix to demonstrate all of the properties and techniques of diagonalization. So first of all, I need to mention that the eigenvalue problem is given in the following way. So we're looking for the vector x, so that if you multiply the a to the x, it is going to be simply descaling this vector. So multiplying the a to the x, it will just change the length of this vector x, so which we can write down as the multiplication of the x to some constant. So the scaling constant is going to be called as the eigenvalue, and this vector is going to be called as an eigenvector. Well, if you are given the matrix for the 2 by 2 case, it is not so difficult to find the eigenvalues. So we are going to use the properties, which basically states that the sum of the two eigenvalues of this matrix should be the trace of this matrix, which is the sum of the diagonal entries, which is equal to the 8. And the multiplication of the two eigenvalues should be equal to the determinant of this matrix, which is equal to the 16 minus 1, which is equal to the 15. So from here, so I would like to ask you, so which values for the lambda 1 and lambda 2 we can choose so that the sum is equal to the 8 and the multiplication is equal to the 15. So probably we can choose 3 and 5, right? So that the sum is equal to the 8 and the multiplication is 15. Now, if I would like to find the eigenvectors x for the given eigenvalue lambda, I'm going to use this equation. So I'm going to take out, I'm going to put the lambda x as the left-hand side and take out the x out of the brackets. And what I will have here is a minus lambda I times the x is equal to the 0. So we are looking for the vectors x, which makes the multiplication to a matrix to be equal to the 0, which is essentially the definition of a null space. So we need to basically find the spatial solutions of this matrix, whose determinant is obviously equal to the 0, to find the eigenvectors. So we are going to do this for these two eigenvalues one by one. So let's try to do this. So first of all, I'm going to find the first eigenvector, which is going to correspond to the first eigenvalue. In order to do this, we need to subtract lambda 1 times the I from the A. So it's going to be 4, 1, 1, 4, minus 3 times this identity, it's going to be 3, 0, 0, 3. So essentially, this operation means we need to subtract the eigenvalue from the diagonal entries of this matrix, which is going to be equal to the 1, 1, 1, 1. Now, the only question is, so how to find the null space of this matrix. So if you remember that algorithmically, you need to bring this matrix to zero echelon form, to find the spatial solutions for this matrix, and so on. But I think for this matrix, it is kind of clear what is going to be the spatial solution on, or what is going to be the vector which is going to make this multiplication to be equal to the 0 and 0. So you see, so both of the columns of this matrix are equal, 1, 1, 1, 1. So this matrix here, so this vector here should contain the two numbers, which are going to combine these two columns in order to get the 0 and 0. And I think we can choose this as minus 1 and 1, so which is essentially subtracting the first column from the second. Or you could choose this 1 and minus 1, which is going to be the subtraction of the second column from the first one, in order to get 0 and 0. So that's going to be the first eigenvector. So the eigenvector, which will correspond to the eigenvalue, which is equal to the 3. So usually we don't really count, so we don't really say that this is the first eigenvalue or vector or the second eigenvector. We usually state that this eigenvector corresponds to this eigenvalue. Now we are going to do the similar thing for the second one. So if we subtract the 5 from the diagonal entries of this matrix A, what we get is minus 1, 1, minus 1, and minus 1. And if you look a little bit carefully to the columns of this matrix, we can see that the columns are the two vectors in the opposite directions, or essentially the second vector, second column, is obtained by just multiplying the first column to the -1. So that's why what two coefficients I can choose as a linear combination of these two columns in order to get 0. Well, I could just simply sum them. So so the sum of these two column vectors are going to give you 0 and 0. And that's going to be the second eigenvector, or the eigenvector, which will correspond to this eigenvalue. So this is how we can find the eigenvalues and eigenvectors, and we're going to use them in order to decompose the matrix. So before we discuss the diagonalization, I would like to discuss a bit about the eigenvalue problem and reveal a couple of its properties and its structural things. So let's say you're given two matrices, which are the square matrices with the same dimensions, and we are given the two eigenvalue equations for both of them. So essentially AX is equal to the alpha x, where alpha and x are the eigenvalues and eigenvectors correspondingly of the matrix A, and bx times is equal to the beta x, which is the eigenvalue problem for the B matrix. So now let's assume that you know all of the eigenvalues of the A and all of the eigenvalues of the B, and you would like to know what are the all eigenvalues of the A times the B. Well, you might guess that this might be equal to the alpha times the beta, and it appears not. And the question is why I'm asking this. Maybe it's obvious that it is not equal to the alpha to the beta. The problem is the following lines of the equations or discussions may lead to you to the confusion. So let's try to find the eigenvalues of the A times the B, knowing the eigenvalues of the A and B separately. So I'm given the A to the B, and I'm going to multiply this to the eigenvector of the B. So we can multiply this three matrices in this case in any order. So if you want, you can multiply A to the B first, then to the X, or if you want, you can multiply B to the X first, then to the A. So obviously we can't really change the places of the matrices. So I can't write like A times the B is equal to the B times the A, but so we can change the order of the multiplication of the three matrices. So that B times the X is going to be equal to the beta X if the X is the eigenvector of the B. So this is going to be equal to A times the beta X. So since the beta is a constant, I can replace the state anywhere else in this equation. So it is going to be equal to the beta times the AX. And if the x is the eigenvector of the A, then A times the x is equal to the alpha x. So it is going to be equal to the alpha times the beta times the x. And if you look to the first equation and to the last equation in this form, so A times the B times the x is equal to the alpha times beta times the x, it is nothing else as the eigenvalue problem for the AB matrix. If you remember, the eigenvalue problem for the A matrix was A times the x is equal to some constant times the x, which is very much similar in this case structurally, right? So we may guess that the alpha times the beta is the eigenvalue of the A times the B, while the statement says no. So the problem is we made some assumptions or mistakes while we are doing this lines of proof. So essentially here we say that x is the eigenvector, is an eigenvector of B. So that's why we could just substitute this with the beta times the x. And a little bit further in the next line here, we assumed that the x is the eigenvector of the A. So that's why we could substitute this with the alpha times the x. So obviously, it is very, so in general, not two, so the two matrices are not going to share all of the eigenvectors, right? So that's why in general, the statement is false. So the eigenvalues of the A times the B is not going to be simply the multiplication of the eigenvalues of the A to the B. But there are cases where all of the eigenvectors of the A are going to be the same as the all eigenvectors of the matrix B. Well, this is when A times to the B. So when A is equal to the B, then they are going to share the eigenvectors. So it is obvious that they're going to have the same eigenvectors, but it appears we can use this in order to understand how the eigenvalues are going to be changed or how we can find the eigenvalues. So let's assume that I'm given the two matrices A and A. So we are given the eigenvalue problem for this matrix A, and I would like to figure out the eigenvalues of the A in the square. So I'm going to write down the A in a square, and I'm going to multiply this as the eigenvector of the A. I'm going to rewrite this as A times the AX. So since x is the eigenvector of the A, I can substitute this AX with the alpha x. It's going to be equal to the A times the alpha x. We may put this alpha in front of this multiplications. It's going to be alpha times the AX. And again, we've got this AX, which is equal to the alpha x. And I can write this down as the alpha in the square times 2zx. And if you compare the first line, the first equation, and the last equation, a in the square times the x is equal to the alpha in the square times the x, it is clear that they are going to have the same eigenvector. So this x is the eigenvector of the a, and this is going to be the same for the a in the square. So if we power up the matrix A, the eigenvectors are not going to change. So the eigenvalues, it appears, are going to change, but we know how they're going to change. So they are going to be simply square root of the eigenvalues of the matrix A. So again, so the powers of the matrix, if you power up the matrices, the eigenvectors are not going to be changed. So similarly to the A in the square, we can write down the equation for any power of the A, where the eigenvectors are not going to be changed. They're going to be the same for the matrix A. And the eigenvalues are going to be simply powered up. So let's say we've got the matrix A in the beginning of the lecture. So with the entries 4, 1, 1, 4, with the eigenvalues to be equal to the 3 and 9. Well, if you square this matrix, the eigenvalues are going to be changed in the way of, it's going to be 9, oh, it was 5 here. So 9 and 25, and the cube of the A are going to have the eigenvalues to be equal to the 27 and 125, and so on. So I just need to power up the eigenvalues. That's it. So I don't need to multiply the matrices to itself many times, then solve the eigenvalue problem separately every time. And also, please note that the eigenvectors are going to be the same. So the eigenvector of this matrix, it is going to be the same for this matrix or for this matrix. And that's beautiful property of the eigenvectors are going to be used in order to easily power up the matrices. So using so-called diagonalization, and now we're going to discuss the diagonalization. So let's say you are given a matrix, which is n by n square matrix, with the n distinct eigenvalues and corresponding eigenvectors. Then for every eigenvalue and eigenvector, we are going to have the eigenvalue problem. So we can write this down in the form of a times the x1 is equal to the lambda 1 times the x1. So this is what definition of the eigenvalue and eigenvector. So the a times the x2 is equal to the lambda 2 times the x2, and so on. A times the xn is equal to the lambda n times the xn. And all of these equations should work together. So what I want is, so you see, so on the left-hand side, you've got a vector which is equal to the vector. So this vector is equal to this vector, and so on. This vector is equal to this vector. So, and all of this is in the system. So it means that you are going to have the n equations for each of them. So the two vectors are equalized. Well, I could just rewrite this in a matrix form. So by just putting all of these vectors as the columns of one vector on the left-hand side, and all of these vectors as the columns of another matrix on the right-hand side. And by equalizing these two matrices, I will automatically equalize the corresponding columns. So essentially, I can write this down in this way. So A times the x1, it's going to be the first column of the matrix. A times the x2 is going to be the second column, and so on. A times the xn. is equal to lambda 1 times the x1, and so on, lambda n times the xn. So these two matrices with n columns each are equal if and only if all of the corresponding columns are equal. So essentially the first column is equal to the first column of this matrix. The last column, for example, is equal to the last column of this matrix, which is the same as this system. So this two writings, so the two equations are interchangeable, so they are the same. So I would like to work with this matrix equation in order to do some transformations to get the diagonalization. So I'm going to take out the A matrix from the columns of all of the columns of this matrix on the left. It's going to be x1, x2, and so on, xn, which is left on inside the matrix. And it is equal to, so you see, so that lambda 1 times the first column, lambda 2 is multiplied to the second column, and so on. Lambda n is multiplied to the last column, where the lambda 1, lambda 2, and so on, lambda n are the constants. So we can write down this matrix multiplication in a form of x1 and so on, xn is going to be multiplied to some diagonal matrix with the entries lambda 1, lambda 2, and so on, lambda n from the right-hand side part. If you remember the matrix multiplication of the diagonal matrices, it was like if you multiply the diagonal matrix from the right, they are going to, so the entries on the diagonal are going to scale the columns. So it is going to be multiplied to the first column, it is going to be multiplied to the second column, and so on, right? So now I'm going to make some notations in order to get the diagonalization simply. So we've got this equation, which is coming from the fact that lambda 1, lambda 2, and so on, lambda n are the eigenvalues of this matrix, and x1, x2, and so on, xn are the eigenvectors of this matrix. So I'm going to denote the whole matrix this with the eigenvectors as the capital X, and the A times to the X is going to be equal to the capital X times to this diagonal matrix is going to be denoted as the lambda. Well, so if all of the eigenvalues of this matrix are distinct, so they are different from each other, then all of the eigenvectors are going to be independent. So therefore, the matrix X is going to be invertible, and by just multiplying both of the parts of this equation to the inverse of this matrix, we can bring this to the form of A is equal to X times to the lambda times to the X inverse. So this is what we call as a diagonalization. We can write down the matrix A, the square matrix with the distinct eigenvalues, as the multiplication of the three matrices which contain the eigenvalues and eigenvectors. So this is going to be called as a diagonalization. So now we are going to do an example of diagonalization of the matrix which we have from the beginning of the lecture and try to reveal the applications of the diagonal matrix. So namely, so how the powers of the matrix A can be found using the diagonalization of the matrix, for example. So again, if you remember, we used to have the matrix A. So I'm going to have we used to have the two eigenvectors and two eigenvalues, right? So I've just changed the order of the eigenvalues, but it doesn't matter because we can just change the order of the eigenvectors in the matrix X as well. So this eigenvector is going to correspond to the 5, so that's why it stands as the first column. And this eigenvector is going to correspond to the 3, so that's why it stands as the second column. So in order to find the full diagonalization of this matrix A, we need to find the inverse of the X. And if I'm going to use the formula to find the inverse of the 2 by 2 matrices, and if you remember, it was like, say, 1 over the determinant of this matrix. So what's the determinant of the X? It's going to be multiplication of this entries on the main diagonal, which is 1, minus the multiplication of this entries on the second diagonal. It's going to be minus 1 times the 1, which is minus 1. So, and if you subtract minus 1 from the 1, it's going to be equal to the 2. So times to this matrix, which is going to be, so simply I need to change the places of the entries on the 1, 1, and 2, 2. And 1, 2, and 2, 1 are going to just change their sign. So it's going to be 1 and minus 1. So that's going to be the inverse. So I'm going to now multiply x as a lambda, then x lambda to the x inverse in order to get whether a is equal to x lambda and x inverse. Indeed. So let's multiply the x as a lambda first of all. So this is going to be 1, 1, minus 1, and 1. Multiply to this lambda, 5, 0, 0, 3. So again, if you multiply diagonal matrix from the right, it is going to simply scale the columns of this matrix. It's going to be 5, 5, minus 3, and 3. So now we need to multiply this matrix, 5, 5, minus 3, and 3, into this matrix. So I'm going to multiply 1 over 2 to here, and I'm going to write 1 minus 1, 1, and 1. So I'm going to multiply this matrices as the, let's multiply this. It's going to be, so I'm going to multiply 1 over 2 right immediately when I multiply this matrices as the row to the column. So the first row to the first column is going to be 5 so plus 3. It's going to be 8 divided to the 2. It's going to be 4. So the first row to the second column is going to be simply the sum of these two numbers, which is 2, divided to the 2 is going to be 1. So the second row to the first column is going to be subtraction of the two numbers. So 5 minus 3 is going to be 2 divided to the 1. It's going to be divided to the 2. It's going to be 1. And this times the second column, it's going to be simply sum of the 5 and 3. It's going to be a divided to the 2, which is equal to the 4. So which is indeed the a. So the multiplication of the x lambda and x inverse is equal to the a.